Our third iteration makes use of an S-shaped acceleration pattern with a 10-second ramp-up time. Deceleration time remains at 0.1 seconds. First, we need to change the acceleration pattern. Navigate to basic function parameter f002, acceleration time, and increment it back up to 10 seconds. Press enter to save the value. Navigate to extended function parameter A097, acceleration pattern selection, and increment it to 0.1, S-shaped curve. Press enter to save this value. With parameter D001, output frequency monitor being displayed, when an operator presses run, the motor drive starts slow, then blows through a pretty wide range of frequencies and kind of backs off the steam when it gets close to the base frequency over a period of 10 seconds. The motor and flywheel undergo a characteristic S-shaped acceleration and speed stabilizes. When an operator presses stop, the motor drive almost instantaneously drops excitation frequency to 0 Hz. The motor and flywheel free spin to a halt just under 6 minutes later. It may help to compare the S-shaped 10-second acceleration with that of our initial linear 10-second acceleration to recognize the subtle differences between them. The linear 10-second ramp-up takes 10 seconds to linearly increase excitation frequency to 60 Hz. Whereas the S-shaped 10-second ramp-up starts off slow, then blows through a wide range, and backs off over the same 10-second period. As a result, for the iteration with the S-shaped curve, the motor and flywheel undergo an acceleration pattern similar to that experienced in an elevator traveling between floors. Here they are together. What remains unexamined at this point is deceleration. The reason I delayed this discussion is because a certain amount of baggage comes associated with it, namely asynchronous generation. You'll recall from way back in the mechanical power, torque, and rotational speed lecture, available at the Big Bad Tech channel, that the rotor with squirrel cage induction motor must necessarily lag the rotating magnetic field produced by the stator for the induction process to work at all. If, however, some external outside force, let's say expanding steam, falling water, moving wind, or in this case a heavy flywheel with established rotational inertia, was capable of turning the rotor faster than the synchronous speed established by the stator, we've effectively turned this motor into a generator. When you get right down to it, that's what the deceleration process is doing. By decreasing excitation frequency, it's slowing the synchronous speed produced by the stator, such that counter-torque or braking action of a generator actively slows the rotor. The problem is there's limits to the amount of energy a motor drive can absorb or dissipate without resorting to accessory components. An especially abrupt deceleration period for a load with an especially large established inertia like this flywheel can easily cause the backfed electrical energy to rise to dangerous levels. Let's see what happens when we try to decelerate this load. First, let's return the drive to the default state, notably a linear 10-second acceleration ramp-up time and a linear 10-second deceleration ramp-down time. With parameter D001, output frequency monitor, being displayed, when an operator presses run, the motor drive linearly increases applied frequency to 60 Hz over a period of 10 seconds. The motor and flywheel accelerate and speed stabilizes as previously. When an operator presses stop, the motor drive starts decreasing excitation frequency, but rather quickly faults out. The motor drive instantly depowers and the motor and flywheel free spin to a halt just under 6 minutes later. Note the alarm LED is lit and the data display is displaying error code E07. When we look up error code E07 in the user's manual, we find it to be an overvoltage alarm, as we'd expect. After the load comes to a halt, a technician can reset the motor drive by pressing Stop Reset. As further evidence of what's going on during this overvoltage event during deceleration, let's monitor the DC link value during the deceleration process. Navigate to Monitor function D102, DC voltage monitor, and press Mode to display the value. At rest, the DC link is just shy of 300 volts. When accelerating, the DC link briefly dips and stabilizes when the motor reaches full speed. During deceleration, the DC link spikes and arrows out at greater than 380-ish volts. Really, the only solution to a motor drive experiencing an overvoltage event during deceleration is to resort to other more exotic braking methods necessitating accessory components, or, much more simply, allowing more time to decelerate the load with established rotational inertia. After some trial and error, I've increased the deceleration time to 13 seconds. With parameter D102, DC voltage monitor, being displayed, the DC link at rest is just shy of 300 volts. When accelerating, the DC link briefly dips, then stabilizes when the motor reaches full speed. During deceleration, the DC link spikes, reaching just shy of 400 volts before returning to a stable at-rest value. Any higher and it would have triggered an overvoltage alarm as previously. Notably, the heavy flywheel decelerates to a speed I can stop with my finger in only 13 seconds, whereas previously I had enough established inertia to rotate for just shy of 6 minutes. 6 minutes of waiting just got reduced to 13 seconds. I would be a happy man if my every whim was granted with this level of expediency. Alright, that's about it for this short applications exercise. In conclusion, we learned to change acceleration and deceleration times and profiles on the Omron 3G3JX-AE004 motor drive and observed their results. Additionally, we learned to recover the Omron 3G3JX-AE004 motor drive from an overvoltage event during deceleration and increase deceleration time to accommodate for loads with large rotational inertia. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.